This is a paper about dynamically instance-guided adaptation, a backward-free approach for test-time domain adaptive semantic segmentation. At first, I will have a quick preview of this paper. So it's a paper about test-time adaptation in segmentation. So at first, I want to illustrate why it's necessary to consider this problem. So we can imagine that we can have a source model before we deploy it, like it's a segmentation model for the autonomous driving. Usually we would gather a lot of data, but when we deploy it, the distribution or target could be very different from the source. For example, we would deploy it in the night time, and we would deploy it when there is rain, and also we can deploy it when there is snow. If we just use the source model, it will cause problem because there is a distribution shift. So normally we would fine-tune the model before deploying it. But the problem is that there are a lot of scenarios that we cannot access to the target data until we met it. Previously, people were trying to increase the generalizability of the source model during the training time. But we can naturally imagine that the performance would not be high because they do not get any information over the target. So in this paper, we focus more on the test time, which means that we can increase the performance of the model during the test time when we are deploying the model. Although there is only a few methods about test time segmentation, there are also some methods for test time classification and some other scenario. So, but they have some problems. We can generally categorize them into three parts. The first one is optimization based, which means that they would update the parameters of the model in some source-free manner. And the second one is instance normalization based, which means that they would change the normalization layer with instance information. The last one is BN statistics updating based, which means that they would update the statistics of the BN layers. They have some problem like they will experience some forgetting and they will suffer from unstable shift or instance, and also about the efficiency and stability. But our method is not updating based, and also we consider both instance and global information. We have two modules. The first one is distribution adaptation module. We would change the BN statistics based on the instance information so that we can adapt it to the specific instance. It was noted that we do not update in the network, so we would not experience the forgetting problem. And also for this part, we do not change the trainable parameters. So it only requires only one-time inference, which is highly efficient. For the semantic adaptation module, which is the second part, with prototype-based method, we consider both global information and instance information. The global information would make the prediction much more stable, but we also introduce the instance information to make it adapt to some specific instance. Here we have an illustration of our method. So imagine that we have two categories, human and cars, and they are in different vital conditions. So in the first step, we only recognize some part of the car, which is in a very good light condition. Then we can use DAM to align the distributions so that some part of the dark area can also be recognized. But the problem is that we can see that there is only part of the human or cars is recognized. Then we can use the prototype-based method, which means that we can use some high confidence area to build the prototype. Although the rest part cannot be recognized by the model, but they may share some similarity with the high confidence areas because they are from the same instance. So based on this, we can use prototypes to find the rest area. So this is our algorithm. They are generally into two steps. In the first step, we would align the distribution with the beyond layers. Then we would calculate the prototypes and give the final prediction. So in these results, we can see that our performance is the best across all combinations of the source and target data. We tested on 3 source domains and try to adapt them into 5 target domains. And on the combinations pairs, our performance is the best. In this page, we present some results of our models and some other methods. We can see that our models would separate all objects much better. Also, we try to provide a very detailed ablation study of our models. So they are categorized into 2 parts. The first one is beyond layers, which is corresponding to the DAM. And the second part is about SAM. We can see that in most of the case, DM and SAM would improve the performance, and the combination of them always generate the best results. Also, we provide some results about the continuous adaptation, which means that we would adapt to a lot of data set one by one. We can see that we attend continuous adapt rates suffer from forgetting problem, which means that the performance will decrease. But our performance is always better than the last experiment is about the efficiency. As has mentioned before, our method do not update the model. So the updating method always have the longest time and memory cost. Compared with Momenta, although they are very efficient because they only update the beyond layers, but our performance is much better. Thanks everyone for watching this video.